Evening, welcome to the sixth live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I'm Harshit Agrawal, a PMRF scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the entire course duration. So, as you're clear about this, these are weekly interactive session that we have every Tuesday from 6 p.m. to 8 p.m. Okay. So, in today's session, we will have a quick recap to the week 5 session that we concluded last week first, and then we will have a review of week 6 learnings. So the week 6 recordings were oriented in continuation to our discussion towards understanding the flexural behavior of reinforced concrete. Okay, so in this we first had a basic overview of what is the effect of axial compression force and its magnitude on the reinforced concrete system, and its response to flexural forces. And then we talked about doubly reinforced section, why reinforcement are added on the compression side, and how we design the moment curvature behavior for such sections. So today, along with the quick theory recap of different segments, I will introduce you with several questions to challenge your understanding on the subject. In total, we will have three questions that we'll discuss today, which are all numerical. And for the same moment curvature analysis that you saw in the course recording of last week, I will show you how to use a simple Excel sheet calculator. You can solve any complex problems easily. Okay, and how we can modify that Excel sheet according to the uh, type of member. Okay, at the end I will make myself available to solve any other queries related to assignment question if there are any other queries. Okay, so last week we started discussing about flexure behavior of reinforced concrete. We talked about how a reinforced concrete beam responds to loading, which induces bending in their geometry. Okay. We talked about the change in the horizontal and the vertical profile, and we talked about compression and tension zones and the presence of neutral axis at which there is zero strain. Okay, so this was that basic overview of axial behavior of concrete that we had. Then we talked about different assumptions of elastic beam theory, like some of them were plane section remains plane section before bending remains plane after bending. This means strain varies linearly with increasing distance from the neutral axis. Okay. Then maximum compression strain in the outermost concrete fiber is taken as 0.0035. Concrete contribution is tension is neglected. So these were some of the major assumptions that we understood. We saw the derivation of curvature and how it is related to strain at a particular section and the distance of that strain section from neutral axis. So for this, we assumed a small element dx at a distance y from the, and in this element dx at a distance y from the neutral axis, we calculated the strain, what will be the strain in the member. Okay, knowing the initial length of this, we wrote the strain as a change in length upon original length, and then substituting these relationships we got the curvature and how curvature is dependent upon strain and the distance from the neutral axis. Similarly, we found out moment of resistance and its relation with curvature. So for a particular cross section, we estimated the total force in x direction and in y direction, and we wrote the moment equation also. Okay. Then using the previous relationship of strain, distance from neutral axis and curvature, we simplified this moment relationship to the final relationship, which was m upon ei is equal to 1 by r, which is equal to the curvature. Okay. We saw how a complex concrete stress block can be, which is parabolic in nature, can be converted into a simplified rectangular stress block using two criterias. First criteria was resultant force should be the same. So whatever force this equivalent stress block is offering, the same force should be offered by the parabolic stress block. Okay, so this both this C and this C are the same. Okay, and second criteria was the location of this resultant force should be the same. So the distance of this resultant force from the neutral axis should be the same. So by you solving these two criterias, we got the value of alpha 1 and beta 1, which will help us to create this equivalent stress block from a parabolic profile. Now, based on strain in steel, when strain in concrete reaches this ultimate value of 0.0035, we saw different types of RC sections. These are under reinforced concrete, under reinforced section, balanced reinforced section, and over reinforced section. So, in a under reinforced section, we say steel yielding is happening before concrete crushing. Okay, so steel will reach its ultimate strain value of say 0.0025 before concrete reaches the ultimate value of 0.0035. Thus, the failure is ductile in nature, and this is what we need for safe evacuation of residents from the building. Okay, we need ductile failure to happen in actual cases also. In a balanced condition, what is happening, this steel and concrete both reaches their ultimate value together. Like steel will reach the ultimate strain of 0.0025, and at the same time concrete will also reach the ultimate strain of 0.0035. Okay, this is the ideal case, but this is not practical. Why? Because the dimensions of the concrete that we require to make these conditions satisfy may not be a whole number in every time. Okay, so this is like not a practical solution. Okay, and in an over reinforced design it is not desired. Why? Because here concrete is reaching the ultimate strain before steel reaches the ultimate strain, so the failure is brittle in nature, and it can be dangerous for the residents inside a reinforced concrete building. Okay, because it won't allow safe evacuation of residents if there is a brittle failure, sudden failure. Finally, we saw the analysis procedure for flexure design. So we know the parameters of a reinforced concrete system. We choose a strain value. We assume a neutral axis depth. Based on the strain value of concrete and neutral axis depth that we has assumed, we calculate the compression stress block element alpha 1 and beta 1. Okay, then we check, okay, then we calculate the strain in steel. So epsilon s we calculate. Okay, we know epsilon c based on strain compatibility, assuming that strain varies linearly across the depth. Okay, so we calculate epsilon s, then we estimate compression force and tension force. Okay, if they both are equal, then the assumed neutral axis depth is correct. Okay, and then we calculate the moment of resistance and curvature. If it is not equal, then we will either increase or decrease x such that we get this condition satisfied. Okay, so for this we saw calculation manually also, and then using an Excel sheet calculator where these things we automated and we were just changing the neutral axis depth. We solved numerical problems of movement versus curvature analysis of RC with the varying reinforcement area and what is the effect of concrete compression strength also. Okay, so this was the part that we completed last week. Okay, now today we'll move towards the remaining 2 points. Okay, so let's start with the effect of axial compression. Okay, so if you remember in the live session where where we discussed about compressive strength of concrete, we talked about multi-axial loading of concrete. Okay, now when a concrete cube is subjected to vertical load in a compression testing machine, we know that the loading surface, suppose this is my loading surface. Okay, so the loading surface, there is a frictional effect between the CTM plates and the concrete which resists the building bulging effect that is created by the loading. Okay, and this is known as end plating effect. Okay, but near the middle this frictional resistance becomes weak, and there are outward stresses that are generated due to this loading. Okay, which results in a cup and cone kind of failure in a concrete. Okay, however, if you apply some axial compression in horizontal direction to concrete, we can provide concrete more resistance against this outward stresses that are building up due to the loading. Okay, and thus we can delay the failure of concrete to a higher peak load value. This is known as axial compression or the effect of axial compression, and this method is popularly used in if strengthening of reinforced concrete using FRP wrapping, okay, fiber reinforced polymer wrapping, where FRP sheets they are wrapped around the concrete to create the axial compression effect, and this strengthens the concrete element. Okay, so you can see in this figure, in the second figure, so the higher is the confining force, more is the higher is this confining force in axial direction, more is the strength of the concrete. Okay, so you can see how the ultimate strength is increasing as we are increasing the confining force on the concrete. And in the third figure you can see that the axial force increases strength only if it is creating a compression effect. Okay, so if this force is creating a compression effect, then only it will increase the strength. If it is creating a tension effect, then it won't increase the strength. So you can see these 3 points where the force was creating tension effect, the strength increment was not, it was, there was no strength increment, there was loss in strength. So these two were the points where there was no confinement effect applied, and these are the points where confinement effects were applied. So this reduces the strength, while when we apply axial compression element, they increase the strength of the member. Okay, so the same concept applies for beam under flexure loading. Okay, so we have this beam, okay, which is subjected to a uniformly distributed load. Okay, if we are applying a axial compression force on this beam, so what will happen? This force will couple with the already existing compression and tension element in acting on any of the cross section of this beam to enhance the load moment or resistance of this beam. Okay, and how it is increasing, that we'll understand now in the ahead session. Okay, so if you see the basic parabolic stress block, okay, of a reinforced concrete, in this stress block we have already seen there is a compression element that is created by the concrete, and this is the tension element that is offered by the steel. Now here we have an additional force element which is coming, which is C dash, okay, due to axial compression. Okay, so this P load that you see here, this is the effect of axial compression that we are assuming here it as C dash. So if we write the force equilibrium equation for this, so the total compression force, we know it is equal to total tension force, so C will now be equal to C dash plus T. So you can see how axial compression is contributing here. Okay, so this additional axial compression force, it is adding up with the tension force of the reinforcement to balance the compressive force of the concrete. So the system in total is capable now of taking more compressive stresses. Okay, since this RHS side is increasing, LHS will also increase. So concrete will be able to take more compression stresses. Okay. Now, if we convert this original parabolic stress block into equivalent rectangular stress block as we did before, okay, the conversion will be the same, but here now there is an additional element of axial compression force C dash, which is acting at the center of the beam. Okay, so suppose total depth of beam is D. Okay, then this force is acting at the distance of d by 2 from the top. Okay, that we are assuming. Okay, so if we write the net moment of resistance along this axis C dash, okay, so along this axis, if I write the net moment of resistance, so what will happen? This compressive force that the concrete is offering and this tension force that the steel is offering, they will make a couple. Okay, they will make a coupling action because they are acting in the opposite direction and they are along the different sides of this neutral axis. Okay, this C dash axis. Okay, so for compression force, the distance of C dash and C, we can write this is beta 1 x by 2. Okay, and this is total distance is d by 2. Okay, so the moment created by the C force, it is nothing but C times d by 2 minus beta 1 x by 2. And similarly, if we write the moment offered by the tension force that is created by the steel reinforcement, this total depth is d and this depth is d by 2. So we can write the moment offered by the reinforcements are t times d minus d by 2, and they both will add up to give us the net moment of resistance offered by the system. So how we proceed with analysis of this section? So again, what we will know, we know the dimension of reinforced concrete, we know the area of steel, we know the grade of concrete, and we know the grade of steel. And in this case, there is an additional element that we will know, that is the axial force, the compression, axial compression force which is acting, which is C dash. Now here again, what we'll do, we'll choose a strain value in concrete, epsilon c, and we'll assume a depth of neutral axis. Okay, any depth we'll assume initially. Now using strain compatibility, we'll find the strain in steel. Okay, once we have found the strain in steel, we will also determine the compressive stress block element alpha 1 and beta 1 based on epsilon c. Okay, because epsilon c dash, it is fixed for us, it is 0.002. Okay, ultimate strain in concrete. Okay, so based on these two values, we will able to get alpha 1 and beta 1. Then we can estimate the compression force. And since we know the strain in steel, if the strain is less than 0.0025, we will use the equation, modulus of elasticity of steel times the strain in steel to get the tensile strength in steel, and we will multiply that with the area of steel to get the tensile force. And if strain in steel is more than 0.0025, we will directly take it as the ultimate strain value. If it is 5, if we 500, then the value will be 500. Okay, then we'll get the tension force. Now in tension force, we will add this element C dash, and we will see whether this is equal to C. Okay, C is equal to T plus C dash. If it is equal, then we can get the moment of resistance and the curvature. If it is not equal, then either we will increase or decrease the X value based on whether compression force is more than or less than the equivalent tension force. Okay, so this is how we proceed with the analysis of a member under axial compression. Okay, so let's see one numerical to understand this effect. Okay, so this is the same section that we solved in the last session. Okay, cross section is the same, and this is a heavily under reinforced section. Okay, now in this we need to find, estimate the moment versus curvature. We need to plot the moment versus curvature profile for different strain values in concrete. Okay, and we have different axial compression force effect also. There is zero axial compression, 10%, and 20% axial compression. Okay, we know the concrete strength and we know the yield strength of steel. Okay, so just give it a thought how we'll do this, and then I will tell you the solution. And in this question again, we'll use an Excel sheet calculator, okay, that we saw in the last class, but just a updated one, how we account for the axial compression also. Okay. So if anyone has any doubt in the discussion that we had till now, you can ask right now. Then we'll start with the question. Just give it a thought how this force element will be considered in the calculation, and then I will tell you. Okay, so let's see the solution. So I will first show you the Excel sheet, like how I have updated the sheet to account for the axial compression force also. Okay, so you can see the sheet. Okay, so initially we know the cross section of the beam, and we know the steel reinforcement area, and we know the axial compression force also which is acting. Okay, what is the thing that is changing for us? The strain in concrete. Okay, so that I am highlighting with blue. Then effective depth we can calculate since we know the cover and the total depth. Okay, and this x value is something that we assume. Okay, Based on the X value using strain compatibility, we get the strain in steel because we know the strain in concrete, we know the effective depth, and we know the neutral axis depth. Okay, if the strain in steel is lower than 0.0025, then so you can see there is a if else loop. If the strain in steel is less than 0.0025, then what I will do, I will use the modulus of elasticity times the grade of steel, and times the strain in steel to calculate the tensile strength. Okay, else it will be 500 or whatever grade of concrete steel we are using. Okay, we know the tensile strength, we know the area of reinforcement, so we get the tensile force offered by the reinforcement. So total tensile force this time will be tensile force offered by the reinforcement per plus the axial compression. So that you can see here. So this is the total tensile force, which is the summation of tensile force plus the axial compression effect. Okay. And for concrete, we will do the calculation similarly as we did in the last session. So we know ultimate strain, concrete strain, it is 0.002. Okay, we know the grade of concrete. Okay, this is all already known to us in the questions. I am highlighting in yellow. Alpha 1 and beta 1 I calculated based on the ultimate strain of concrete and the concrete strain which is there in current condition, and we get the compressive force element of concrete. Okay, if these two values are equal, then we will take this moment of curvature, moment of resistance, and the curvature value. Okay, so in the moment of curvature also you can see I have two elements. This element is this element is offered by steel. Okay, and this first element it is offered by the concrete part. Okay, similar to what we saw here. Okay, so same equation I have written as a formula here, and for curvature it is simple x by y. Okay, epsilon by x. Okay. Any doubt in this sheet? Is it clear to everyone? Okay, so let's see the solution now. Okay, so for first case is for zero axial compression force. So first I will just check whether the inputs are right or not. Okay, so rectangle wheel cross section is 300 cross 500. It is here. Cover is 50 mm. So D value,
Sir, how to assume the x value?
X value we'll see right now. I will solve this question completely. So you will get to know how we are assuming X value. Okay.
Okay, sir.
Okay, so I'm just checking right now whether the inputs are right or not. The basic inputs that is given. Okay, grade of concrete is 35 MPa. Area of steel is 750. That was mentioned in the question. Okay, so we'll start with solving this question. Okay, so first case for us is when the strain of concrete is 0.0005. So what I will do, I will fix this concrete strain as 0.0005 here. Okay. Now we don't know what is the depth of neutral axis. So first of all, whenever you start solving, just assume it as d by 2. Okay, so d is 450. So 450 by 2 is 225. Okay, so you can see here in this table, I have assumed the depth of neutral axis is 225 initially. Okay, so what is the strain in steel? We can see strain in steel is 0.0005. So that is what I have written here. What is the net compression force? It is 541.41. Okay, so this is I am highlighting in green. Okay, net compression force, it is coming out to be 541.41. So that's this what I will write here. And net tension force is 1125. Okay, now this is not equal. Compression force is not equal to the tension force. So we know if we will increase the value of x, the compression force element will increase. Okay, if we'll decrease the value of x, the compression force element will decrease. Okay, so what we'll do, we'll change the x value. Okay, so I guess there's some mistake here. Huh. This axial compression right now it is zero. Okay. By mistake I wrote as 1050. Okay. So right now there is no axial compression acting on this member. Okay. So this value I have kept as zero. Okay. So net tension force is 75. Okay. Not 1125. Okay. Now what I will do? My compression force is more than the tension force. So what I need to do, I need to decrease the value of x. Okay. So I will start changing the value of x here. I will set it at 200. So when I change to 200, you can see again compression force is still more than the tension force. So I will further decrease it to 175. At 175 also compression force is more than the tension force. So I will further decrease x. 150. At 150 still it is more. 125. Still it is more. 100. Now you can see the compression force is smaller than the tension force. Okay. This is total tension force. Okay. So what we need to do, we need to increase the value of x by a small quantity, by a small value, because we need to increase the compression force now. Okay, so I will set it at 104. Okay, so if you see at 104, the total tension force and total compression force, they are nearly equal. So that's why I chose 104 here. Okay, now what is the strain in steel at 104? When x is equal to 104, it is 0.00166. What is the net compression force? It is 250.25. What is the net tension force? It is 249.52. What is my moment? It is 103.59. And what is the curvature? It is 4.81 e minus 6, 10 to the power minus 6. Okay, so this is how we can use this simple Excel sheet to do this iterative work of changing the neutral axis depth very quickly. Okay, we'll see one more example so that you understand. Okay, now I will change the concrete strain to 0.001. Okay, again, I don't know the depth of neutral axis, so I will take it as 225. So you can see what is the strain in steel, it is 0.001. What is the total compression force? It is 984.38. So I will write here as 984.38. What is the total tension force? It is 150. Okay, now compression force is way higher than the tension force. So I need to decrease the value of x. So I will directly go to 100 this time. At 100 also, you can see compression force is more than the tension force. So I will decrease it further to 80. However, at 80, you can see compression force, it is now lower than the tension force. So what I will do, I will increase the value of x. I will set it at 85. 85, you can see we are getting close, but still compression force is less than the tension force. So I will just do a small increase, 85.5. It is again less. I'll again go 85.8. Now you can see we are very close. Okay, it is almost the same if we round off. Okay, so we can assume the neutral axis depth is 85.8. What is the strain in steel at this depth? It is 0.0042. So this means that the steel is yielding in this case, and it will happen. Why? Because this is a very heavily under reinforced section, so steel yielding will happen before concrete crushing. Okay, so net compression force was 375.38. Net tension force is 375. Moment is 157.57, and curvature is 1.16 e minus 5. So I will just write it as 11.6 into 10 to the power minus 6. Okay. Similarly, we'll do for 0.002. Okay. So are you clear now how we are deciding the neutral axis depth? Someone asked me this doubt right now, right? Khushbu,
Yes, sir.
you are
Yes,
clear?
sir. Yes, sir.
Okay,
Yes,
so
sir.
I shared with you this Excel sheet, if I remember last time. Just try to edit that sheet with this additional force element and try to solve this question with me.
Yes, sir. I have received it.
So you just make this edit, na? Add these two additional elements so that you can calculate the total tension force in that. Okay, or you can
Okay.
do that after the session also. Right now, just solve the question with me.
Okay, sir.
Okay, so we'll do the same iterative process for 0.002. Okay, again we'll take x as 225. Okay, the strain in steel is 0.002. The total compression force is 1575. total tension force is 300. So we know we need to decrease the compression force. Okay, so I have done this iteration work. Okay, so I will directly write the value at which this both will become equal. So it will, if you take the neutral axis depth as 53.5, you will see the net compression force and the net tension force, they will get very close to each other. Okay, and this at this depth the strain in steel is 0.0148. Okay, so strain in steel is 0.0148. This means since this is more than 0.0025, it means that the steel is yielding. Compression force is 374.5, tension force is 375, and the moment is 161.11. Curvature is 37.3 into 10 to the power minus 6. Okay, now again for 0.0035, I will just change the concrete strain as 0.0035. I will set the X value as 225. Strain is steel is 0.0035. Compression force is 1722.66. 1722.66. Tension force is 375. So my compression force is way larger than the tension force. I will need to decrease the value of X. So I will set it at 50. At 50, still compression force is more than tension force. I will set it at 49. So you can see now compression force is very close to the tension force. The strain in steel is 0.028. Steel is yielding. Okay. Compression force is 375.16. Tension force is 375. Okay. And at this strain value, moment is 160.52 and curvature is 771.42 e minus 5, e minus 6. Okay, 10 to the power minus 6. Finally, we'll do the same thing for strain value of 0.004. Okay, so 0.004, again we'll do the iteration 225. The compression force is 1575, tension force is 375. Compression force is way larger than the tension force, so we need to change the value of X, we need to decrease X. I'll set it at 53.5. Then you can see compression force is nearly equal to the tension force. Okay, so this value is 0.202964. Compression force is 374.5, tension force is 375, moment is 158.61, and curvature is 74.77 e minus 6. Okay, so in this way, for axial compression element, when axial compression is 0, then we can find moment and curvature at different concrete strain. So you can choose more strain values also. Just for demonstration, I took 5 points. Okay, now I have 10% axial compression force which is acting. Okay, so 10% of the total compression capacity of concrete. So total compression capacity of concrete is nothing but the grade of concrete times the gross area of concrete. So that's why how I calculated P. P is 10% of FC times AG. AG means the gross area of concrete. So it is zero point 0.1 into 35. Okay, grade of concrete it is 35 MPa. Okay, and total area of concrete it is the depth, total depth times the width, so 300 times 500, and I have divided by 1000 to convert Newton into kilonewton. So this axial compression element 10%, it will come out to be 525. So what we'll do now in the sheet, okay, so in the sheet we'll just write here 525. Okay, so you will see this total tensile force, it will now be summation of this tension force plus this axial compression force. Okay, so again we'll do the same iterative process. Just a second. Okay, so we'll set the concrete strain at 0.0005, X at 225. So you can see tension force is 600, compression force is 541.41. Okay, So compression force is 541.41, tension force is 600. So this shows us that compression force is less than tension force. So we need to increase the value of x. So I will increase it to 240. Again, compression force is small. I will change to 244. Now we are getting very close. Compression force and tension force are becoming very close to 244.5. So at 244.5, we can see they are almost equal. Okay. So x, the neutral axis depth, it is 244.5, and at this depth, the strain in steel is 0.00042. Okay, so this is 0.00042. Compression force, it is 588.33. Tension force is 588.04. Moment is 110.65, and curvature is 2.04 into 10 to the power minus 6. Okay, similar iteration we'll do with 0.01. Okay, so this is just an iterative process, but it will be done very quickly because of this automated calculation sheet that we have created. Okay, so at again at 225 it is 984.38 compression force. Tension force is 675. Okay, compression force is more than the tension force, so we need to decrease the value of x. So upon iteration you will find at 174.25 both will be almost equal. Okay, so steel strain in steel right now it is 0.0058 158. Since it is less than the yield strain, this means that concrete is failing. Okay, compression force is 762.34, tension force is 762.37. Okay, moment capacity it is 191.57, and curvature it is 5.74 into 10 to the power minus 6. Okay, again for strain value of 0.002. Okay, at what 225, compression force is 1575. Tension force is 825. We need to decrease the compression force, so I will set this x value at 128.5. At 128.5, the strain in steel it is becoming 0.005. Compression force is 899.5. Tension force is 900. So both are almost equal. So moment capacity we can take now 256.53, and curvature it is 115.54 into 10 to the power minus 6. Okay. Similarly, we'll do 4.0035. Okay. At 225, 1722.66. 900, we need to decrease the compression force. So this x value at 117.5, you will get strain in steel is 0.009, compression force you will get 899.61, and tension force will be 900. So they both are almost equal. So this moment we can take 252.34. Okay, and curvature is 2.29.78 into 10 to the power minus 6. And for the last case, I will directly give you the values at neutral axis depth, which at which compression force and tension force are equal. Okay, so when you will set this x value at 128.5 for concrete strain of 0.0024, you will get steel is yielding. Okay, now because strain in steel is more than the yield strain. Okay, compression force is 899.5, tension force is 900, moment capacity is 242.08, and curvature is 3.11, 31.12 E minus 6. Similarly, if I will increase the axial compression force further, so this time it is 20% now for the third case. So 20% of the gross compression capacity, zero point 0.2 into 35 into 300 into 500 will give me the compression force divided by 1000 I have done to convert Newton into kilonewton. So again in this sheet I will just change this value as 21050. Okay, Again for 0.0005, when the strain will be neutral axis depth will be 437, you will find compression force and tension force are equal. Okay, and at this depth, the compression force is 1051.53, tension force is 1052.33, moment capacity is 106.67, and curvature is 1.14 e minus 6. Okay, similarly I will just do the calculation here for you. At strain value of 0.001, when my neutral axis depth was 264, the compression force and tension force will be equal. Okay, so again here steel strain is 0.0007, compression force is 1155, tension force is 1155.68, moment is 203.16, and curvature is 33.78 into 10 to the power minus 6. Okay, at strain value of 0.002, neutral axis depth at balanced condition it is 102.5, compression force is 1417.5, tension force is 1416.67, so they both are almost equal, so we can take the moment as 320.07 and curvature as 9.87 into 10 to the power minus 6. For concrete strain of 0.0035, the neutral axis depth will come out to be 1686 for balanced condition. Okay, concrete strain is 1424.6. This is 1425. This is 1424.06. Okay, both are almost equal, so new moment is 311.82 and curvature is 18.81 into 10 to the power minus 6. And finally for the last point, at concrete strain of 0.004, the neutral axis depth will be 203.5, and at this depth you will find tension force and compression force are almost equal. Okay, compression force is 1424.5, tension force is 1425, moment will be 286.18, and curvature is 19.65 into 10 to the power minus 6. Okay, so this is how we can do calculations at various compression elements very easily if we will use a Excel sheet as a tool for calculation. And now what is the effect, like what we understand from this, you can see here in this slide. Okay, so this was our element, okay, that we took, the reinforced concrete element. Okay, here initially compression was 0%, 10% and 20%. Okay, so for these three cases you can see how the moment versus curvature profile will look. So this is for 10%, okay, 0%, then the red one is for 10% and the blue one is for 20%. So you can see as we increase the axial compression on the concrete, what is happening, the moment capacity of the concrete it is increasing, and the curvature of the concrete it is decreasing. Okay, so this is the effect of axial compression. It is making concrete able to handle, it is able to handle more resistance, okay, against bending moment. Okay, so from 0 to 10% there was a drastic increase, from 10 to 20 there was a less significant increase. Maybe if we go from 20 to 50%, we may not see more much change in the profile also. And one more point you can see, this these were point where the concrete reaches the ultimate strain of 0.0035. So the second last point. So you can see as we go above the concrete crushing strain, the moment capacity starts to decrease again. Okay, and from 0.002 to 0.0035 also we saw there is very slight decrease in the moment capacity, or it is almost equal. Okay, but above 0.0035 there is a decrease in the capacity that happens, okay, irrespective of the session. irrespective of the section. Okay, so everyone are clear with this question and this analysis of axial compression? Any doubt in this? Any doubt with this Excel sheet, how we were using this for calculation? Okay, so this was about axial compression. Okay, now the last part to understand in flexure design is the effect of compression reinforcement, or what we commonly say as doubly reinforced section. Okay, so if we understand what doubly reinforced section means from a stress strain profile, so in the first figure you can see how a doubly reinforced sections looks like. Okay, so there is reinforcement on both sides. So there is tension side reinforcement also, which has a effective depth D, and there is reinforcement on the compression side also, which have a effective cover of D dash. Okay, so now in the strain distribution, it remains the same. Okay, we follow the assumption of elastic beam theory, which says that plane section remains plane after bending. So we have strain varying linearly across the neutral axis. However, in the stress diagram, apart from the tension force element T and the concrete compression force element Cc, we now have an additional element Cs, okay, which is due to the compression reinforcement. Okay, so the total compression force offered by this section, it is Cc plus Cs, and this will try to balance the total tension force, which is T. Okay, and similarly the total moment of resistance, now it will be the compression force offered by the concrete times the lever arm distance of concrete plus compression force offered by the steel times the lever arm distance of steel. Okay, now why we are providing compression reinforcement? Okay, that is important for us to understand before moving into the analysis. So generally, as we have discussed, when we design a reinforced concrete to resist any flexural loading, we prefer a under reinforced section. Okay, why? Because under reinforced section, they fail in a ductile manner, and that is a safe failure which helps the residents from inside the building to evacuate if the building is experiencing any collapse. Okay. However, suppose the area of steel on the tension side is not enough to make to support certain bending moment. Like for example, in a balance section, we know the moment of resistance is 200 kilonewton meter, and the external loading. Okay, so suppose this is my beam. Okay, and it is subjected to some external loading. Okay, now when I am providing reinforcement, balanced reinforcement, I am getting the moment of resistance of this section, it is 200 kilonewton meter. Okay, suppose this external load P, it is creating a moment, bending moment of 250 kilonewton. Okay, 250 kilonewton meter. So we can't use this balance section design anymore, or a under reinforced section design anymore. So we have two options now. Either we need to change the dimension of the section, okay, this concrete section, to support the moment, or we need to increase the steel reinforcement area. Now, suppose the first option is not possible, maybe due to some site constraint or infrastructure constraint, and second option we can't take, because if we will increase the area of reinforcement further, we'll move from balanced section to an over reinforced section, and we don't want a over reinforced section. So for such cases, we provide compression steel. Okay, so as written in the first point, the compression steel is needed when the capacity of a singly reinforced section is less. Okay, so if we are providing steel only on the tension side, it is not meeting the capacity, okay, or the resistance that we want. Okay, and how it deals with loading, it transfers the load to the compression steel. So then additional steel that we are providing here, what this will do, the additional moment that has been created, it will transfer the moment to the compression steel, which will help us to deal with this loading. Okay, there are other benefits also for providing compression steel, like it reduces the creep in concrete. Okay, it reduces the stress in concrete since there is reinforcement now in the compression side also, which can take stress. There is less sustained load deflection. Okay, so if you see the deflection at the midpoint under sustained loading, as we'll increase the compression steel, the deflection at the midpoint also it decreases. Okay, and it helps in construction of reinforcement cage. So since we are providing reinforcement on both the sides, so if you look at the cross section, so there are two reinforcement here, three reinforcement here, so we can easily create a reinforcement cage using this reinforcement without providing any dowel bars on the side to hold the stirrups. Okay, and most importantly, why we are using compression steel, we are using it to avoid the over reinforced design, and that is helping us to change the failure mode from compression to tension. So compression failure is a brittle failure, tension failure is a ductile failure. Okay, how we do this? By providing additional steel on the compression side. Okay, so whatever steel I require for the balance condition, the additional steel that I require, I am providing at the compression side so that this section can remain as an under reinforced or a balanced section, and still it can take more bending moment. It can resist more bending moment. Okay, so if you see from the basic parabolic stress block, we have now an additional element CS, which is coming from the compression state. And when we convert, okay, so the net a force equilibrium equation, how we'll write it is CS plus C is equal to T. So the additional compression steel force, it is adding with the compression force offered by the concrete to balance the tension force of the reinforcement. And in this way, the member is able to take more stress. Okay, now if we convert the original stress block into a equivalent rectangular stress block, the dimensions, the calculation will remain the same. However, now there will be just one additional element CS due to compression steel. So if we write the moment of resistance equation along this line T, so we know it is the force times the lever arm distance. So C into its lever arm distance, which is D minus beta 1 x by 2. And for CS, this depth, it is given as D dash. Okay, so it will create a lever arm distance of CS into D minus D dash. So this total depth is D. Okay, so this depth will be D minus D dash. Okay, and they both will help add up to give the net moment of resistance. Okay, so when we talk about analysis of such sections, how we do, again as we did in the last question, we know the concrete elements and we know the reinforcement area and we know the grade of steel and concrete. And now there is one more thing that we know the compression steel area also and its cover. Okay, so we'll choose a strain in concrete, we'll assume the neutral axis depth. Using strain compatibility, we'll find strain in steel in both tension side and compression side. Okay, we will use the effective stress block element to get alpha 1 and beta 1 value, and we'll estimate the total compression force and the tension force. If this equation T is equal to C plus CS it satisfies, then we can calculate the moment of resistance and curvature. If it doesn't satisfy, then we do the iterative approach to set the value of X until this condition is reached. Okay, so this is how we do the analysis. Okay, any doubt in this part, like of why we are using doubly reinforced section and how we calculate moment of resistance and curvature with the doubly reinforced section? Okay, so let's start with the basic question first. Okay, so in this question, we are not forming any curvature profile or anything. In this question, we just need to determine whether our section is over reinforced or under reinforced. Okay, so what I have given in the question, I have given to you a rectangular beam having cross section of 300 cross 500 and it is heavily under reinforced. Okay, okay. It is reinforced. Okay, I should not write heavily under reinforced here. Is reinforced with the AST of 500 meter square at the bottom. Okay, with an effective cover of 50 mm. Okay, now we need to determine the type of section. Okay, what is the type of section if my AST is this, and we need to comment whether compression steel reinforcement should be provided or not. Okay, we know the, you know the grade of steel, you know the grade of concrete, so just try to do the calculation how you will determine whether this section requires compression steel or not. Okay, just give it a attempt, find which type of section is this, what is the balanced reinforcement area, and whether the reinforcement area that we have provided, it is more than the balanced reinforcement area or less than balanced reinforcement area. Okay, so I will mute myself for a couple of minutes. I will let you people give it a try, and then I will solve the question. In the meantime, if you have any doubts, just type in the chat box. So was anyone able to calculate what is the balanced reinforcement area? Or can anyone tell me how we'll do the calculation for balanced reinforcement? So was anyone able to calculate what is the balanced reinforcement area or how we'll do that calculation? Can anyone unmute and just tell the procedure how how we'll determine the type of section?
Sir, first we have to know about if it is a balance section, then what is the value of x, and I can find 262.8, 262.5. After finding x, we are assuming that this section is balance section. Then we have to calculate the force by concrete is equal to force by steel. Then force by steel AST we don't have. AST into 500 is equal to alpha into beta 1 into x into fc into b. Then we
Yeah.
can calculate
Okay,
AST.
yeah. Whatever you explained, it was perfectly correct. Okay. So let's see that calculation now for others also. Okay. It was perfect, whatever you told. Okay. So this I am just moving here. Okay. So as he said, okay, what we need to determine? Okay, to determine the type of section, okay, we first need to find the condition for balanced reinforcement. Okay, condition for balanced section. Okay, so if we can determine what is the area of steel required for a balanced section, then judging whatever amount of area of steel that we have provided, we can compare. If this 1500 is less than the balanced reinforcement area, then this section is an under reinforced section. If 1500 is more than balanced reinforcement area, then it is an over reinforced section. And if 1500 is equal to the balanced reinforcement area, then it is a balanced section. Okay, so how we can determine? So for a balanced section, what we know, the strain in concrete is equal to 0.0035, and at the same time the strain in steel is equal to 0.0025. So both concrete and steel are reaching their ultimate values together. Okay, so the depth of neutral axis we can calculate. Okay, it will be 0.00235 upon x equal to 0.0025 divided by d minus x, so 450 minus x. Okay, so when we'll rearrange this and solve, we'll get x is equal to 262.5 mm. Okay, so we know the depth of neutral axis. Okay, now we need to estimate stress in steel. Okay, so since steel is reaching the ultimate yielding point, okay, the strain in steel is reaching 0.0025. So my tensile strength I can write is 500 MPa. Okay, and the total tensile force will be this 500 times AST, whatever area of steel it has. Okay, so AST is right now unknown to us. Now how to find AST? We know one more condition: the total tension force is equal to the total compression force. Okay, so we need to calculate the compression force. Okay, so compressive stress, so for for stress in concrete. Okay, we first need to find the equivalent stress block parameter. Okay, we don't know the equivalent stress block parameter right now. Okay, so how we can do that? So we have the equations. Okay, I will just copy the equation from the earlier discussion. Okay, we had these two equations. Okay, one is alpha 1 times beta 1 is equal to this. I will just paste it here. Where is our solution? Okay, and second equation is beta 1 is equal to this. Okay, now in this equation, epsilon c we know it is 0.0035, epsilon c dash is 0.002. Here also I will change epsilon c is 0.0035, epsilon c dash is 0.002. So upon solving, we can get the value of beta 1 here. Okay, so value of beta 1, it will come out to be 0.90. And when we'll substitute this here also, so again epsilon c 0.0035, epsilon c dash 0.002, and here also epsilon c 0.0035, epsilon c dash is 0.002. Okay, and beta 1 we know zero point 0.9. So upon solving, you will get alpha 1 value will come out to be 0.81. Now we know alpha 1 and beta 1, so we can get the value of C, total compression force. It is alpha 1 times the grade of strength of concrete, which is 35 MPa, times beta 1 zero point 0.9, times neutral axis depth 262.5, times b, the width of the member 300, and I will divide by 1000 to convert Newton into kilonewton. So this value will come out to be 2009.31 kilonewton. Okay, now we know total tension force, we know total compression force. So this total tension force is equal to total compression force. So this is equal to 2009.31 kilonewton. So upon equating, you will get area of steel AST will be equal to 4018.6 mm square. Okay, now this area for balance section, it is more than the area that we have provided right now. So this means that our section is an under reinforced section. Okay, so I can write here it is a under reinforced section. Okay, and since it is an under reinforced section, we don't need to provide compression reinforcement right now. We can provide reinforcement in the tension side only. Okay, everyone clear with the solution? How we determine whether we need compression reinforcement or not? Any doubt in this? Yeah, your calculations are right. Okay, now I have one more question for you. I said for an under reinforced section we don't need to provide compression reinforcement. What if I provide compression reinforcement? Whether it will increase the moment of resistance capacity?
No, sir. I think no, because all
Can
the
anyone
tension
else?
is
Okay, you are saying no. Okay, can anyone else share their opinion? And why no? Just give me reason.
because tension capacity is borne by tension steel only.
Yeah,
That's why.
okay. See, the
If tension
reason
steel
is
is
it is an under reinforced section. So yielding in the tension side, the steel which is yielding in the tension side is governing the design. So irrespective of the amount of compression steel you provide, the design is controlled by the steel in the tension side only. So you won't see much change in the moment curvature behavior. Okay. And this was one numerical that you saw in the NPTEL session. Okay. So if you remember, you saw a professor solved one question where for an under reinforced section he provided compression steel. So suppose this question that we saw right now, okay, in this question I am providing compression steel, okay, of same area as there in tension side. So this compression steel is also of area of 1500 mm square, okay, and this is an under reinforced section, okay. So you can see if you will do the moment versus curvature analysis for this, you will see there won't be any change in the moment capacity of the member, though the curvature is reducing because the creep in concrete is reducing because of steel present on the compression side. The moment capacity is not changing because failure is still governed by this, okay. And since this will yield much before the yielding will happen in the concrete, then the capacity, the moment capacity won't show any significant change. Okay, so that's why we say we need compression steel only when the section is an over reinforced section, so that we can convert the section into an under reinforced section. Okay, clear with this point? Any doubt in this concept? Okay, so such tricky questions they can appear like one may ask you to like define this member for as a doubly reinforced section, but you need to check whether it is needed or not, whether I can further increase the steel in the tension side only, or whether I need to provide steel now in the compression side. So this area right now was 1500. The balanced reinforcement area is around 4000. We still have room for around 2500 mm square of steel that we can place in the tension side. So better we'll go with that placement only rather than going for placing steel in the compression side. Okay. Now let's see. suppose I have a over reinforced section. So we know the balance reinforcement area was 400 4,000. Now I have a section which has a reinforcement of 7,500 mm square. So this is clearly a over reinforced section. Okay. Now in this over reinforced section, when I provide steel in the compression side, what is the effect? Okay. So this is the numerical that will show us that effect. Okay. So the section remains the same. Okay. The cross section of the dimensions of the concrete remain the same. The steel area is now 7,500 mm square, and we want to plot the moment capacity versus curvature profile for various strain values in concrete. Okay, and for various compression steel reinforcement. So initially compression steel is 0, then it is 0.25 times the tension steel, then it is zero point 0.5 times the tension steel. Okay, and the concrete grade and the yield strength of steel is remaining the same. So for this section, what will be the effect of compression reinforcement? Okay, that we'll see in this numerical. Okay, so this again will solve with the Excel sheet calculator. Okay, we'll modify the Excel sheet again this time. So just think what all modification will be needed now. Just tell me. Okay, so last time you saw we just added one more element, the axial compression, and we added it to the tension force to calculate the total tension capacity. Now in this question, when we are doing a design for a doubly reinforced section, what all changes we need to do? Can anyone tell me? So what will be the process now? Suppose I give you that the strain in concrete is 0.002. How you will proceed ahead? Just think.
Yes, sir. In Excel sheet, I think we have include uh, compression steel capacity
How you will include that?
CC. We have to find strain in compression steel.
Okay. So how you will do that?
Yeah.
Okay. So let's see the sheet. Okay. You are going in the right direction. Let's see in the sheet. Okay. So you can see this second sheet. Again, I know the cross section. Okay, you can mute yourselves now. Okay, I know the cross section of the concrete. Okay, I know the area of reinforcement that I've provided on the compression side, and I will know the area of reinforcement that I am providing on the tension side. So this is tension reinforcement, this is compression reinforcement. I know the strength of steel, I know the strength of concrete. Okay, these all things that I have highlighted in yellow, this I know. Concrete strain is something that I'm changing. Okay, so as we did in the previous question and in the last session, I know the concrete strain, I know the effective depth, that is total depth minus the cover. So I will assume a neutral axis depth and I will get the strain in tension steel. Okay, based on strain in tension steel, I can get the tensile strength of steel. And I know the area of tension reinforcement, so I get the total tensile force now. Okay, offered by the steel in the tension side. Now what about steel in the compression side? Okay, so I know the cover for steel in the compression side. Okay, d dash I know. Okay, I can calculate the strain in the steel in the compression side also. How you will do? Again from strain compatibility. So if you see, okay, so if you see this strain relationship, what will happen? This at the depth d dash, I have my compression steel. Okay, this is at a depth d dash. Okay, so these two triangle, this triangle and this bigger one triangle, they are also similar triangle. So what I can write, and the strain in compression steel I am denoting by epsilon cs. So epsilon cs upon x minus d dash is equal to epsilon c 0.0035 upon this x, neutral axis depth. Okay, so using this relationship I can get the value of epsilon cs also, the strain in steel for known strain in concrete. So this right now it is 0.0035, or we can write in general it is epsilon c. Okay, so from this we will get the strain in compression steel. Okay, once we know the strain in compression steel, if the strain value is more than 0.0025, then the steel is yielding. If it is less than 0.0025, then again we'll calculate the strength of steel by multiplying the strain with the modulus of elasticity, which is 2 into 10 to the power 5. We know the area of compression steel, so we can get the total compression force offered by the compression steel. Adding this compression force with the compression force offered by the concrete, we will get the total compression capacity of this doubly reinforced section. And now this total compression capacity, okay, if it is equal to the total tension capacity of the member, then we can calculate the moment of curvature, moment of resistance and curvature. Okay, so this is how we proceed with the question. Everyone clear with this sheet and whatever modification I have done here? Any doubt in this? Any doubt in the modification in this Excel sheet that has been done? And how we are proceeding with the solving a doubly reinforced section. Okay, so first of all we will assume a strain in concrete. We'll take a strain in concrete and we'll assume a depth of neutral axis. Okay, now with the assumed depth of neutral axis and strain in concrete, we'll calculate strain in both compression steel and tension steel. Once we know the strain in both compression steel and tension steel, we can calculate the tensile force offered by both compression steel and tension steel. And we know how we calculate the compressive strength, compressive force offered by concrete. So we know all the three forces, so then we can equate and check whether it is a uh, whether it is in equilibrium or not. If it is not in equilibrium, we will change the value of x accordingly. Okay, I hope it was clear. Any doubt in this? Okay, if there is no doubt, let's see one numerical to understand. Okay, what is the effect of compression reinforcement? Okay, so in this numerical, first is when there is no compression steel, then what is happening? Okay, so I'll just set the conditions here. Okay, compression steel area, I will take it as 0. Okay, so you will see this effect of compression force, it is 0 right now. So this whole block here, which I am highlighting, it is of no use right now because area of compression steel is 0. Okay. BD, this is set, cover is set. Okay. My concrete grade, it is set, and the area of reinforcement is 7,500. So again, iterative approach, I will take concrete strain as 0.0005. I'll assume depth of neutral axis is 225. Okay. At 225, what I'm getting, compression force is 541.41. Tension force is 750. So I need to increase the compression force. Okay, so I will increase the value of x. So I will change it to 250. At 250, you can see they are almost equal. Okay, so compression force is 601.56 and tension force is 600. And at this neutral axis depth, what is the strain in steel? It is 0.0004. So steel is not yielding. Okay, so what is the moment here? Moment is 219.43. Curvature is 2 into 10 to the power minus 6. Okay. Similarly, we'll do the calculation at other strain values also. So for strain in concrete at of 0.001, again neutral axis depth is 0.225. I will take initial assumption. Okay. Compression force is 984.38, tension force is 1500, so I need to increase the compressive force element, so I will increase the depth of neutral axis. This time I will set it to 257. So at 257 you will see compression forces 1124.38, tension forces 1126.46. Okay, and strain in steel is 0.00075. So steel is still not yielding. Okay, and this both forces elements are almost equal. So I can assume this neutral axis depth is correct. Moment capacity is 404.83 and curvature is 3.89 E minus 6. Okay. Similarly, now for strain value of 0.002 at 225, compression force is 1575, tension force is 3000. 1575 and 3000. I need to increase the value of x. So I will increase the value of x to 274.5. So at 274.5, compression forces 1921.5, tension forces 1918.03. You can further refine this. Okay, if you want, you can just change the value of x further. So you can set it at 275. At 275, compression force is becoming larger than the tension force. So at 274.6, again it is becoming shooting. So that's why I have taken 274.5, because this is the closest that we are getting. Okay, at 274.4. Okay, 274.4 will give much closer value. Okay, so compression force is 1920.80, tension forces 1919.83. So this is almost equal. Okay, so at this strain compression strain value, at this neutral axis depth, the moment is 666.71 and curvature is 7.29 into 10 to the power minus 6. Now when concrete reaches its ultimate strain value of 0.0035, if I assume neutral axis depth is 225, compression force is 11722.66, tension force is 3750. Okay, now compression force is way less than the tension force. I need to increase the depth of neutral axis. I will change it to 310. So you'll see at 310, compression force is 2373.44, tension force is 2370.97. They are almost equal. So moment is 736.95 and curvature is 111.30 into 10 to the power minus 6. And at this strain value in concrete, what is the strain in steel? It is 0.00158. Okay, so you can see this 0.00158, it is less than 0.0025. So this means that concrete crushing is happening and steel is still not yielding. So this is the behavior of a over reinforced section. Now suppose I increase the strain in concrete further, okay, to 0.004. Assuming the depth of neutral axis is 225, I will get compression forces 1575, tension forces 3750. So I need to increase the depth of neutral axis. I will change it to 326. You will get compression forces 2282, tension forces 2282.21. They are almost equal, so we can take the moment of resistance. So it is 654.93 and it is 12.30 E minus 5, E minus 6. Okay, so you can see when we go beyond the ultimate strain in concrete, we can see the moment of resistance, it starts to decrease again. Okay, rather than increasing, it starts to drop. Okay, and at this strain value, steel strain is still less than the yielding strain. Okay, the steel is still not yielding. It is the concrete crushing which is dictating the section capacity, and that's why the moment is decreasing significantly. Okay, beyond the ultimate strain of concrete. Okay, so this was when there was no compression steel. Now what if I provide a compression steel of 25%? Okay, so ASC is equal to 25% of AST, so that will be 1875. So what I will do in this sheet, I will just add area of compression steel also now. So you can see now this whole section where we are calculating compression force element of compression steel, force element of compression steel, it will become active. And the total compression force, it will be summation of compression force of concrete plus compression force of steel in the compression side. Okay, so this 3291.5 value, you can see this is coming from addition of this block plus this block, and this value now should equate with the tensile force capacity to get a balanced to get an equilibrium condition. Okay, so again I will set concrete strain is 0.0005, so I will directly do the calculation for balanced condition. So when you will set the neutral axis depth at 3232, you will see the compression force is 705 point, the strain in compression steel, it is 0.00039. Okay, the compression force, net compression force, it is 705.34, and the net tension force, it is 704.74. They both are almost equal. Okay, I will copy this here in the second block. Okay, moment of resistance, it is 265.90, and curvature, it is 2.16 into 10 to the power minus 6. Now I will increase the strain in concrete. I will set it to 0.001. Okay, now for this balanced neutral axis depth will be 238. So at 238, the compression net compression force is 1337.47, 1337.47. Tension force is 1336.13. Moment is 500.31. And curvature is 4.20 into 10 to the power minus 6. Similarly, we'll further increase the concrete strain to 0.002. Okay, and for balanced condition, now we'll set the neutral axis depth to 251.7. So you'll see at this depth, compression force, net compression force is 2362.91. Tension force is 2363.53, and the moment capacity is 866.96. Curvature is 7.95 into 10 to the power minus 6. Okay, similarly, when concrete reaches the yield strain value of 0.000035, okay, the neutral axis depth for the equilibrium condition, it is 282.5. Net compression force is 3100.39. Net tension forces 3112.83. Moment capacity is 1073.34, and curvature is 12.40 E minus 5. Now, when concrete is reaching the ultimate strain value, the steel strain in the tension side, it is lower than 0.0025. So you can see how by providing reinforcement in the compression side, we can make steel yield before okay, steel right now, it is still not yielding when concrete is in the because this is an over reinforced section, because we are not lowering the area of steel. Okay, so in this question we have kept the section over reinforced, and then we are providing additional reinforcement. So that's why here you will see concrete crushing is still happening, because it is an over reinforced section yet. Okay, if you want to design it as under reinforced, what we need to do, we need to decrease the area of steel, and we need to keep the compression steel. Okay, so that part we'll see in the next session when we talk with design using is code. Okay, so steel is not yielding, both in both the style, both the side, steel is not yielding. Okay, here the steel strain is lower than 0.0025, here the steel strain is more than 0.0025. So the steel on the compression side, it is yielding now, rather than steel in the tension side which is yielding. Okay, now at the final point at 0.004, okay, when the neutral axis depth is 299, you will see the equilibrium will be reached. The compression force, it is 3030.5, and the tension force will be 3030.1. Total moment capacity, it is 1003.95, and the curvature is 13.4 into 10 to the power minus 6. So similar to the case that we saw without compression steel, you can see once the concrete passes the ultimate strain value, the moment capacity starts to drop, because here still concrete crushing is dictating the uh, capacity of the member, and that is the limitation of an over reinforced section. Okay, there will be sudden drop in the capacity of the member because of its brittle nature, because concrete is governing the design. Now suppose I provide more amount of compression steel, now 50%. So what I will do, I will just change this area to 50%. So that is 3750. Okay. So I'll just give the calculation of values quickly. So at concrete strain of 0.0005, neutral axis depth will be 216.5. So you can see at this neutral axis depth, total compression force is 809.35. Okay, total tension force is 808.89, moment capacity it is 311.34, and curvature it is 2.31 e minus 6. Okay, I increase the concrete strain to 0.001. Okay, the neutral axis depth upon iteration you will get 221.5 for balance section. The total compression force it is 1549.76, 1549.76. Total tension force it is 1547.40. The moment of resistance of this member is 593.23, and the curvature is 4.51 e minus 6. Okay, similarly for the last three part, when concrete strain reaches 0.002, for balanced condition, my neutral axis depth is 232.5. So at this depth you will see compression force is 2804.92, tension force is 2806.45, moment of resistance is 1061.45, and curvature is 8.60 into 10 to the power minus 6. Now when concrete reaches the yielding strain value of 0.0035, at for equilibrium condition, the depth of neutral axis is 245. Okay, the compression force is 3750.78, tension force is 3750, almost equal at this value. Moment capacity is 1387.30, and curvature is 114.3 e minus 6, 14.30. Okay, and finally when we go beyond the ultimate strain of concrete, what we'll see, the neutral axis depth for equilibrium it is 268. Okay, now the compression force is 3751. Total compression force, total tension force is 3750. Moment capacity it drops 1342.82, and the curvature also increases further 14.9 into 10 to the power minus 6. Okay, so how we interpret this data? By plotting their compression plot. So you can see here in this diagram. Okay, so in this diagram this section remains the same, this AC is increasing. Okay, it is changing from 0 to 25% to 50%, okay, of the total tension reinforcement. So you can see how the profile is changing. Okay, so what is happening here, as we increase the area of steel in the compression side for an over reinforced section, what is happening, the total moment of resistance capacity is also increasing. Okay, and the curvature of the section is also increasing. Okay, so instead of using axial compression, in axial compression what we saw, the moment of resistance capacity was increasing and the curvature was decreasing. But here in this case what happens, the curvature also increases because we are increasing the area of steel in the entire member. So that's why curvature increases. Okay, steel is yielding. Okay, that is giving more curvature to the system. Okay, so this is the effect of area of compression reinforcement. Okay, for an over reinforced section we will see the change. However, for an under reinforced section we will see there won't be any change in the profile. Okay, Any doubt in this question? How we use the Excel sheet to do the calculation and what was the end interpretation of result? Any doubt? Okay, so this is like something that you need to practice on your own. So I have just shown you today how you can use this Excel sheet for simplifying the calculation. So if you will do these calculation manually using a pen and a paper, you will find it very difficult. Okay, it will consume a lot of time. However, once you will get used to doing calculation, like not in exam you won't be able to do such calculation, but for your practical application or in on site or for just for your learning, if you're doing calculation, it will be very easy for you. Okay, so if anyone wants these sheet, they just drop me a mail. Okay, last time I shared the mail ID to you, I will again share this time. Okay, so if you want these Excel sheets, you can just drop me a mail. Okay, just copy this mail ID and you can drop me a mail, I will share you the sheet. Okay, and try to use this sheet because this will give you a lot of knowledge. We are not just calculating the moment and the curvature, we are able to see how the force, net force in the tension side and the compression side is changing. What is the strain in steel when the strain in concrete reaches a particular value, whether steel is yielding or not, whether concrete is crushing or not. A lot of interpretation you can get from this sheet. Okay, and what is the effect of area of reinforcement, you can check. What is the effect of area of compression steel, like in this case, you can check. What will be the effect of changing the depth of neutral axis, that also you can simulate on your own. Okay, so suppose instead of giving a cover of 50, I gave a cover of 75, then how the things will change, that also you can check. Okay, any doubt in the discussion that we had today in the axial compression and in the compression steel part? Did everyone understood how we solve, how we plot moment curvature behavior?
Yes, sir, we understood.
Okay, just try to practice this. Yeah, because these are just iterative things. I would have given you one point, do the calculation, that doesn't make sense until we see the entire story. Okay, at a particular concrete strain, what is happening, that is not important. At different strain, how the profile is changing, how the capacity of the member is responding to the system, that is important for us.
Sir, for doubly reinforcement, if the tensile strain of steel is yielded, means it is under reinforcement, but we put more reinforcement in compression side, and we get the strain in compression still is less than 0.0025. Then this section is what? It is under reinforced section or
See,
over
right now,
reinforced
see,
section?
this was an over reinforced section. I'm not saying this is an under reinforced section.
No, no, no. Not about this, sir. Not about this.
About this
If
previous.
any, no, no, no. About some other problem
Okay,
I
just
am
repeat. I
solving
will
that.
just try to repeat.
Yeah, for any doubly reinforced section, if tensile tension reinforcement is tension reinforcement strain is more than 0.0025. Okay, means
Okay.
it is under reinforcement, but we put more compression still in compression side, and the compression strain of steel is less than 0.0025. Then this section called what? It is under reinforcement or over
See,
reinforcement?
this is an under reinforced section. Why? Because yielding in the tension side is governing the design.
Okay, okay, sir.
Okay. That is what you are asking now.
Yes, yes, yes.
Okay. How we dictate whether it is an under reinforced and over reinforced section, it depends upon which is yielding first, whether concrete is yielding or steel is yielding. Okay, when concrete reaches the strain value of 0.0035, what is the strain value in the compression side, in the tension side? Okay, that will show
Intense.
dictate the
Okay.
type of section. Okay, so what we do to avoid a over reinforced section where concrete compression side will fail before tension side, we reduce the area. Okay, we keep the area under a balanced section and we add reinforcement in the compression side. Okay, that helps us to increase the moment capacity without converting the section from an under reinforced to an over reinforced. Okay, so that calculation, for that we'll see in the next session how we use IS 456. Okay, and how we do that calculation. Okay, these things that you saw here, it was post design thing. Like, suppose you have designed the element. Okay, you have chosen the dimensions of concrete, you have chosen the area of steel that you want to provide, everything you know. Now you want to know in actual field condition how this element or this section will respond. So for that we are plotting moment versus curvature. Okay, under a sustained loading condition, as the strain in the member will increase, how, what will be the response? That was what we have discussed in the last two sections. Now, using IS code, we'll see how we choose the area of reinforcement that we need, okay, for a particular moment capacity, and how we take a under reinforced and an over reinforced section, that we'll see in the next session. Now, clear?
Yes, sir. Yes, sir.
Any other doubt to anyone? Okay.
No, sir. Oh,
Okay, so this was all about today's session, and this, with this we'll end the this moment curvature analysis part. Okay, so this base for flexure member. So we had a basic overview today of flexure behavior of reinforced concrete when axial compression is introduced. We saw through numerical how the magnitude of axial compression affects the moment curvature. So we saw as we will increase the magnitude of axial compression, the moment capacity will increase and the curvature will decrease in the member. We discussed about doubly reinforced section, why they are needed, and how compression steel reinforcement affects the stress strain relationship that we saw. We looked into why compression steel is not provided, not needed for an under reinforced section, and how area of compression steel affects the moment curvature behavior of an over reinforced section. So in over reinforced section, we saw if we'll increase the area of compression steel, the moment capacity will increase and the curvature will also increase. Okay. So this was all for today's session. Thank you.